Alright everybody, welcome back. Today's video scope is we're going to be talking about what malloc is, then we're going to be talking about allocators, and then we're going to be talking about RSS versus your heap, and then we're going to do a case study on a handbrake PR that I put up a couple of weeks ago that looks like it's circling the drain now, and then I'm going to give some final thoughts. Okay, so for starters, how does memory allocation work? So programs need memory to work, and the OS owns all the memory. So in order for the program to get memory, it needs to talk to the OS through something called a syscall. The issue is that syscalls to the operating system are very slow. So typically you'll use an abstraction on top of a syscall. For example, printf is abstraction on the syscall write. But in the case of memory management, we'll use something called an allocator. So an allocator will act as the middleman between your program and the OS. So such as malloc or free are example of allocators. In the case of handbrake, glibc is our allocator, and the malloc and free equivalent is gmalloc and gfree. Little diagram on the right here about kind of memory, how memory flows. So next up is how free works. So by calling free, the memory will go back to the allocator's pool of memory. And once it's in the allocator's pool of memory, it's up to the allocator to decide whether it wants to hand the memory back to the operating system. This is about just kind of like efficiency, where it's like if you ask for 64 bytes, you're probably going to want another 64 at some point. So it tries to kind of hold on to that so it can just give it to you straight from the heap. And I've also talked to someone who's way smarter than me, and he said it could be also something about data structure alignment as well. It might be worth looking into that if you are interested. So next up, I want to talk about the mmap threshold. When you call malloc, you're going to pass in an integer, and your integer is going to represent the amount of bytes of memory you want. So for example, when you call malloc 64, because it's such a small amount, malloc's going to give it to you on the heap. And if you wanted something even like a little bigger, like 100 megabytes or 100 bytes, or excuse me, 100,000 bytes or so, it's still underneath a cutoff, and the cutoff is for using mmap. So what mmap is it's a syscall that maps a file or device directly into the process's virtual memory. It's important for this case because it'll automatically return to the operating system when you call free. So for example, in this last malloc call, so when you ask for 4 megabytes worth of memory, it's going to be over the malloc's cutoff, and it's going to put it on mmap, and then you'll get the behavior I mentioned earlier. So glib takes this a step further and provides a dynamic mmap threshold. So glib's whole goal is to improve speed, so it tries to avoid using syscalls as much as possible, such as mmap. So glib assumes that when you want to free a big block of memory, that you'll want to claim it again eventually. So it'll keep that block ready on the heap so you can access it easily. But then it also will raise the cutoff of when to use mmap. So basically, when you have repeated free calls, it'll cause that threshold to balloon up, which is not a bad pattern at all, but in this case, it gave us some issues. So next up, let's talk about RSS. So when you run top in like your Linux terminal, for example, and it says a program is using 7 gigabytes of memory, it's usually referring to RSS. And what RSS is resident set size. And that basically is telling you how much physical RAM the operating system is currently handing out to a process. So RSS only counts the memory that the allocator is holding, and it doesn't take into account the memory the allocator has freed. But so for example, if you call free, but glibc still is holding on to your memory, your RSS will stay high. So when you see a growing RSS, it doesn't mean that there's a memory leak. Always, at least. Sometimes, obviously sometimes there is. So what is a memory leak? A memory leak is an unreachable reference to an allocated block of memory. The only way to get it back is by killing your process. On the other hand, memory retention is different because free was used correctly, but the allocator just didn't give the memory back to the operating system for reasons that we discussed earlier. And then the tricky part is by looking at something like top, for example, you wouldn't know the difference between a memory leak and memory retention. Okay, so moving on to the handbrake case study bug kind of deal. So real quick, handbrake is an open source video transcoder. And then just a quick high level overview of the code base. libhb is the shared C engine for decoding and filtering and coding and stuff of that nature. But when it comes to the front end, there's 3 different stacks here. Use GTK on Linux, use Coca on Mac, and WinGUI on Windows. So then the bug, as you can see on the right here, was basically that when you click live preview with the SVT AV1 encoder on a Linux build, it would cause memory usage to spike in a staircase pattern. So for example, like what he was saying and what I observed, every new preview generation will add 100, or not 100, 1 or 2 gigabytes of RAM without ever cleaning back up for itself. And later in the issues, the different contributors were talking, and they noticed there was no leak on macOS. Which something to note is that both macOS both use that libhp library that I was talking about earlier, or libhp engine or something. So it would have to be something Linux related, and they flagged it as a Linux UI bug, and I decided I would give this a stab and pick it up. So real quick, what does that play button do? So a static preview is 1 frame, but a live preview is a couple of seconds worth of frames. So it'll use your actual settings and your actual encoding pipeline to kind of give you a demo, I guess a live preview. So every time you press live preview and you played your couple of frames, SVT AV1 wouldn't the SVT AV1 encoder would give you 1 or 2 gigabytes of memory. We know there's an issue with memory usage, but we don't know exactly what. So I kind of tested a couple of things, and this is kind of a table of what I tried. So first things first, it was tagged a Linux UI bug. So is it the GTK UI? So if you test it with an X264, which is another encoder, it doesn't staircase up like it would with the SVT AV1 encoder. So you can rule out it's not the UI. So then, is it the encoder itself? No, it's not, because if you run the encoder by itself, it'll use only about 1 gigabyte. So you can rule that out. Does it leak per frame? No, it's a flat 1.1 gigabytes when you use a CLI encode. Is there a memory leak? If you use something like heap track, you'll notice not too much memory ends up leaking, so you can write that off. And then what about if you had repeated codes in libhp? And then the answer is yes, that's where the issue lies, because it will climb up in like a staircase pattern. And with that, I was able to reproduce the issue. Okay, so let's talk about how I was able to reproduce this. So leveraging Claude, I had it build a headless libhp reproducer. So it was decoupled from the GTK front end. And basically what that did was it scanned once and then encoded the same clip 15 times on one persistent HP handle call. Memory usage climbed steadily with every encode, which reproduced the bug. Then we ran heap track on that reproducer and noticed that the live peak heap was about 1.5 gigabytes, which was expected, as we know, because it allocates 1 or 2 gigabytes per encode. And basically no memory was leaked. So knowing that the RSS value was continuing to rise by gigabytes with every encode, so if we remember that the RSS was rising by gigabytes with every encode, there's really one more subject that we could point to. glibc was hoarding all the memory. So here's how this worked. On the first preview, the 1.5 gigabyte buffer goes to mmap, as expected. But when it's freed, glibc will raise its dynamic memory threshold. Okay, so after multiple previews, the threshold ends up getting really big. So now the buffers are going onto the heap. And like I mentioned earlier, so due to how heap works, once a buffer will get like buried in a pile of memory, it'll no longer be able to be returned to the operating system, because you can only return the top element on a heap. So every preview, the RSS will increase because of that reason. So why was this a problem with only Linux? So we know the contributors couldn't reproduce it on Mac, so it was a Linux issue. And the reason why is because Mac builds use different allocators compared to like a Linux build. So the allocator on Mac, for example, would return a large free blocks of memory to the operating system, whereas glibc ended up not doing that. Okay, so we know the issue, but how do we prevent this from happening? So basically we want to pin the dynamic threshold that we were talking about earlier. So we do that by calling malloc option, or mallopt. Here we can address the mmap threshold and the mmap trim threshold. In this case, we did about 1 megabyte. And basically what this is telling us is that anything bigger than 1 megabyte is going on mmap. So it returns the OS when you call free. So now the encoder won't really put anything on the heap anymore. So now every time you use the encoder, you won't really put anything on the heap anymore, which is nice. So then once your encode gets finished, you want to call malloc trim, and this is just going to return the memory back to the operating system. But if you notice here and here, you have these if-defs for glibc, and that just makes it so it only runs on Linux builds. Okay, so why choose 1 megabyte as a threshold? So basically the reason why is mmap is slower than heap for reuse. So you really want to find a good balance between performance and speed. So I mapped out 5 values here, and just kind of like looking at this, we chose 1 megabyte, as you can see, because it had low RSS growth, but it also had a really good wall time. So using something like 256 kilobytes would give you the best performance, but as you can see, it's a little bit slower than using a megabyte. And using something like 8 megabytes ends up giving you the best speed, but look at the RSS growth between a megabyte and a gigabyte. Like, it's like almost 10x or maybe 9x or so, or maybe 8x, whatever that ends up being. I can't do the math right now. So yeah, 1 megabyte is just a good middle ground between all the other options. So there's about a 1.1 gigabyte baseline, and then when you call malloc trim only, you can get that growth per encode down to about 330 megabytes. And then when you use the full patch with malloc trim and plus malloc option, you can get that down to 15 megabytes, give or take, per encode. And if you look at this graph here, you could take note that before it was staircasing up. This is the staircase I was referring to earlier. So every time you encode, you add another gigabyte or two to the staircase. And eventually, like about here, it was like going to crash my computer pretty much because I don't have a lot of RAM on this machine. And as you can see, that was 1, 2, 3, 4-ish encodes. But if you look at my patch, it uses the same memory per encode, as you can see here and here, but it returns memory back to the OS so that when you're ready to call the next encode, it doesn't staircase it up like it did over here. So you're able to call, like I have 1, 2, 3, 4, 5 encodes, and I could do this all day without any issues. So things I want to take from this example, first things first, memory can balloon for reasons that aren't leaks. Well, I feel like when you're in school, you talk a lot about memory leaks, and you never talk about memory retention. I had no idea this was even possible until I took on this issue. In that same vein, free doesn't always give memory back to the OS. Also, RSS counts all the memory that your allocator hoards, and it's not like categorized or whatever. So, and then when I went to go tackle this issue, I really liked that I used AI to build a simple reproducer. This just let me kind of break the problem up into smaller bits. So instead of using all of handbrake with all the moving parts, I was able to just take the parts of handbrake that I needed to take and then have like something simple that I could run repeatedly without any issue. And then also, when you tackle something like this, you really just want to experiment. The guy in the original PR said he only tested it with SVT AV1. So when I tested it with X264 and I found there wasn't an issue there, we kind of like had an idea of what path to go down. And then also, something not working on a specific platform makes it relatively easy to pinpoint what it could be. You really have so many options of where something could be, and they're all in the, what makes Linux build different than a Mac build. Okay, so where's this PR sitting at? So we were waiting for the next version of the encoder to come out. Recently, I think maybe yesterday or the day before, version 4.2.0 came out, and that new version attempted to reduce the number of small allocations being made. So I gave it a test, and when tested, the RSS growth did improve. It's about 10% less on the version 4.2.0 over 4.1.0. But if you look down here, as you can see, when you apply my patch to both versions, the growth is significantly less than an unpatched version. So hopefully my patch will get merged in soon. I wanted to get this video out now, just I don't really want to wait on this getting merged or whatever. I'll link the PR in the description. If there's more to it, I'll make a follow-up video. If it ends up kind of just getting merged, you can check it out there. All right, that's all I have for this video. Thank you guys for watching, and I hope everyone has a good rest of their day.